find the basis for the row space of matrix A, the column space of matrix A, and the null space of matrix A. And here we are given this beautiful 3x4 matrix. And so, to find the row space and the column space of matrix A, we can row reduce the augmented matrix with the 0 vector to echelon form. So to find the bases for the column space of matrix A and the row space of matrix A, we are going to row reduce the augmented matrix A with that 0 vector to echelon form. And then we'll be able to use that theorem we just looked at to find the basis. So here we go. Taking our given matrix here, we have 1, -1, 5, -4, 2, -6, 9, -4, 10, and then -7, 1, 7. And we're augmenting this with the 0 vector. So looking at our first pivot here, we want to use this to eliminate the entries below it. Give ourselves plenty of room. So we can do two operations here. We'll do the first row plus the second row to attain the new second row. And then we'll also go ahead and do -5 times the first row plus the third row to attain the new third row. And so let's see what this gives. The first row will remain the same. That's still 1, -4, 9, -7. And then adding the first and second row, we end up with 0, -2, 5, -6. And then we have -5 plus 5 is 0. +20 minus 6 is +14. -45 plus 10 gives us -35. And then last but not least, 35 plus 7 gives us 42. And looking at our third row here, we realize we have a greatest common factor of 7. So let's scale the third row by 1/7, which produces the equivalent matrix 1, -4, 9, -7. We have 0, -2, 5, -6. And then we have 0, 2, -5, +6. And so looking at this reduced matrix here, we realize that the second and the third row are the same. We have a redundant row here. So we can use our second pivot to eliminate the entire third row. So we're simply just adding the second row and the third row to produce that new third row. And this leaves us with 1, -4, 9, -7, 0, -2, 5, -6, 0, 0, 0, 0. And so this is our matrix in echelon form. So we're going to pause for a cause here and think about what this row equivalent matrix, which we could even go ahead and say this is matrix B in echelon form to the given matrix A. So what is this telling us? Well, we can say that by the previous theorem that we just verified, we know the following. We know that the first two rows of matrix B, those two non-zero rows, form a basis for the row space of matrix A. So the first two non-zero rows of matrix B, that matrix in echelon form, form a basis for the row space of matrix A, as well as the row space of matrix B, because they are a common space. So we can further conclude or state our final answer that the basis for the row space of matrix A is defined as set B, and this is equal to the row vectors 1, -4, 9, negative 7, and 0, negative 2, 5, negative 6. And so this is our beautiful final answer for the basis for the row space of matrix A. So now, what about the column space of matrix A? So let's begin by recalling that to find the column space of matrix A, we need to identify the pivot columns of matrix A in that echelon form. So fortunately, we just row reduced matrix A to echelon form. So let's observe that matrix B has a pivot position in the first column and the second column. So since we already know that matrix A is row equivalent to matrix B, then column 1 and column 2 of matrix A form a basis for the column space. And so we can say that therefore the basis for the column space of matrix A is defined as the set B containing the column vectors 1, negative 1, 5, and negative 4, 2, negative 6. And so this is our beautiful final answer here for the basis of the column space of matrix A. And last but not least, we now need to find a basis for the null space of A. So we can recall that to find the basis for the null space, we want to find that general solution in its parametric vector form. So to do that, we're going to continue with this row reduction to rewrite matrix A in its row reduced echelon form. And we're almost there. We've already reduced matrix A to echelon form. So we just need to take this a little bit further. So looking at our second pivot here, we want to eliminate the entry above it. So we'll do negative 2 times the second row plus the first row to attain the new first row. And so this is equivalent to the matrix 1, 0. We have negative 10 plus 9 leaves us with negative 1. Positive 12 minus 7 is 5. And then 0, negative 2, 5, negative 6. And the third row is still all zeros. So now we just need to simplify our second pivot, and we'll do that by scaling the second row by a scalar of negative 1/2. And we're left now with the equivalent matrix 1, 0, negative 1, 5, 0, positive 1, negative 5/2, positive 3, 0, 0, 0, 0. And so rewriting this as a linear equation, we have x sub 1 minus x sub 3 plus 5 times x sub 4 is equal to 0, and x sub 2 minus 5/2 x sub 3 plus 3x sub 4 is equal to 0. And of course, keeping in mind that we want that general solution in the parametric vector form, let's rewrite this to make clear what are the basic variables and what are our free variables. So basic variable number 1, x sub 1, is equal to x sub 3 minus 5 times x sub 4. Our second free variable, x sub 2, is equal to positive 5/2 x sub 3 minus 3 x sub 4. So those are our basic variables, and we'll make a note to ourselves that x sub 3 and x sub 4 are both free. So we can say, therefore, our general solution for vector x in parametric vector form is defined. We have vector x in R4, x sub 1, x sub 2, x sub 3, x sub 4. So this is equal to, we have x sub 1 is equal to x sub 3 minus 5 times x sub 4. We have x sub 2 is defined as 5/2 x sub 3 minus 3 times x sub 4. X sub 3 is free, and x sub 4 is free. So if you see it, by all means, go for it. If not, don't forget you can incorporate zeros into those columns so it makes separation easier. And let's give ourselves plenty of room. So we have, factoring out the free variables, I have x sub 3 is multiplied by the column vector 1, 5/2, 1, 0. And then we have the free variable x sub 4 multiplied by the column vector -5, -3, 0, 1. And this is, of course, such that x sub 3 and x sub 4 are scalars. So remember that the basis for the null space of matrix A are these two column vectors for our free variables. So the basis of the null space of matrix A is the set B, defined by the column vectors 1, 5/2, 1, 0, and -5, -3, 0, 1. And so this is our beautiful final answer here for the basis of the null space of matrix A.